let's now conclude the mathematical induction side-by-side examples. So I already proved equation 1 in another video from the side-by-side examples. Now I'm going to prove equation 2 from the side-by-side examples. Finish proving it. So just as a quick recap, this is the equation I'm trying to prove. How does induction work? Well, first you show that the equation you're trying to prove works for n equals 1, or some starting point. So if I plugged 1 into the left-hand side, I got 1/2. I plugged 1 into the right-hand side, I got 1/2. Okay, so this equation is true when n equals 1. Next, I replace n with k in my equation, and I go ahead and I'm saying, okay, k is some fixed number, and I'm assuming that my equation is true up to this point k. It for sure is true for the number 1, but now I'm assuming it's true up to some number k. What you do with this equation is you want to prove the next step. Assuming this is true, you want to prove the next step. So on the left-hand side, I add the next term. Okay, so in my assumption, I stopped here. But in my challenge, I'm going to add the next term. So I'm going to take it to the next step. Before I stopped with k times k plus 1 in the denominator. And now I take it to the next step where I have k plus 1 and k plus 2 in the denominator. And on the right-hand side, since I've added this k plus 1 term, I have to recalibrate everything. I have to kick everything up one step. So my numerator goes from being k to k plus 1. My denominator goes from being k plus 1 to k plus 2. And now I use my assumption to simplify this challenge equation that I'm trying to prove. Notice that according to my assumption, this whole chunk here is equal to k divided by k plus 1. Right, that's what this is saying. So I replace this whole chunk here of my challenge equation with k divided by k plus 1. I call this my challenge equation because this was what I'm trying to prove. If I can now prove this, I'm done. So let's go about proving this equation. What I need to do, though, is let's just highlight this equation. I'm going to need to get rid of this recap just for space reasons. So I'm going to take this highlighted equation. I'm just going to rewrite it here by itself. And again, I'm going to use my same trick. I want to get rid of the denominators. So I'm going to say this is equivalent to, and then I go ahead and multiply through by the least common denominator. The least common denominator, or however you want to think about it. I'm going to multiply through by k plus 1 times k plus 2. And why do I do that? Because this k plus 1 times k plus 2 is going to cancel out this k plus 1 in the denominator. It's going to cancel out this k plus 1 times k plus 2 in the denominator. It's going to cancel out this k plus 1 in the denominator. And it's going to give me something a little more practical to work with. So I'm going to get rid of my denominators. And again, this is legal. You just want to say this is equivalent to, and then you go ahead and cancel out your denominators here. So what happens if I hit this with k plus 1 times k plus 2? Well, this k plus 1 is going to cancel out the k plus 1 in the denominator. However, it's going to leave this k plus 2 left over. So basically, I'm going to have k plus 2 times k. And these k plus 1s canceled each other out. What happens if I hit this with k plus 1 times k plus 2? That's actually easy, because these completely cancel out, and I'm just left with 1 all by itself. On the right-hand side, what happens? The k plus 2's cancel, and I'm left with this k plus 1 times this k plus 1. Okay, so this is what happens after I multiply through. Alright, let's just get rid of the color coding. So, again, this is what we have, and I just get rid of the color coding. So we have this now. And the same deal. This one I don't think you can quite as easily just do in your head. I think the most direct way to prove that this is true, and again, this is what you're going to do for most induction problems. It's the brute force method of proving something. Is you simplify the left-hand side, see what you get. Simplify the right-hand side, see what you get. And if you get equal, and if you get the same things on the left-hand side as you get on the right-hand side, then the equation is equal. So let's do that with the left-hand side. Here's the left-hand side. What am I going to do here? Well, to simplify this, I'm going to distribute the k. So k times k is going to give me k squared, times k times 2 is going to give me 2k. Alright, so this goes here. This becomes this simply by distributing the k. But now that I've distributed my k, I don't really need the parentheses. So I end up with k squared plus 2k plus 1. That's what my left-hand side simplified to. Let's try my right-hand side now. So I'm going to take k plus 1 times k plus 2. I'm sorry, k plus 1 times k plus 1. I'm going to do the same thing. I'm going to distribute the k. So if I distribute the k, I get k squared plus k. Okay, that's where this comes from distributing the k. Now I distribute the 1. 1 times k is k. 1 times 1 is 1. Okay, so if I multiply this out, I get k squared plus k plus k plus 1. I have two k's here, so if I add them up together, I get plus 2k. Okay, notice the left-hand side equals the right-hand side. This worked. We're done now. Just as a recap, we start with this. We go through the hoopla of showing that, okay, it's true for n equals 1. Here's our assumption equation. This is the equation that we're trying to prove. Okay, after some simplification, this is the equation that we're trying to prove. And we proved this equality by clearing the denominators and then showing each side of the equation simplifies to the same thing. So that's what we did. That's it.